In this video, we're going to go over Skill Sheet 4.1 acceleration problems. Well, this was our homework that was assigned on Sunday, and so let's go ahead and take a look at how to solve these problems. Remember, when we do a constant acceleration problem, you're looking for words like acceleration, that's number one, or you're looking for units, the unit of acceleration, which is meters per second squared, or some unit of distance per unit time squared. You're also looking for a change in velocity. Okay, so if your velocity increases or decreases, right, that would be a way. So these are the three ways you can tell that it's a constant acceleration problem. And when it is, you will immediately make a list of 5 variables. Delta x tells you how far. V and V naught would be final and initial velocity. That tells you how fast. This is, of course, the acceleration. And T tells you how long it takes to do something. So you want to make sure that you know how to list your variables appropriately. When you do a problem, you're guaranteed to have 3 of the 5 variables known in the problem and 2 of them unknown. When we do a constant acceleration problem, we're going to use the GUESS method. GUESS is an acronym that stands for the following. GU in GUESS stands for step 1, which would be make your list of givens and unknowns. Step 2, the E in GUESS stands for equation. Choose the correct equation based on the list of givens and unknowns. Step 3 would be to solve and substitute into the equation and get an answer for your unknown. Let's take a look. Oh, and as a side note, these are the 4 constant acceleration equations we're going to be using for this exercise. Number 1 was already done for us. Okay, so let's skip down to number 2. Okay, we can see that a skater increases her velocity from 2 meters per second to 10 meters per second in 3 seconds. What's the acceleration of the skater? So we are going from 2 meters per second to 10 meters per second in 3 seconds. And we want to know what the acceleration is. And that is the major unknown. This is the who cares variable. And we don't need to know delta x. We're only looking for acceleration in this one. So you can see that using that v, v naught, a, and t are the variables given to us in the problem, we can see that we would be using this first equation right here. Well, we write the equation down, v equals v naught plus a times t. Now we need to solve this equation for acceleration. So to solve for acceleration, you need to get rid of the v naught and the t. Now to get rid of v naught, okay, v naught is a positive v naught. So to get rid of v naught, you need to do the opposite of the positive and you need to subtract. So we're going to subtract v naught from both sides, just like that. In which case we have v minus v naught equals a times t. Okay, then what we do is we then need to get rid of the a, or the t, excuse me. We're solving for a. So to solve for a, we need to get rid of the t. Now you'll notice that a and t are being multiplied times each other, right? A, t means times. So what's the opposite of times? We need to divide away what we're trying to get rid of. Okay, and we end up with the following equation. We end up with acceleration equals final velocity minus initial velocity over time. And if you paid attention to the beginning of the assignment, you can see that equation was given to us right here at the top. Well, now we go ahead and plug in. The final speed was 10 meters per second minus the initial speed of 2 meters per second over 3 seconds, and the acceleration, let's see, 10 minus 8, or excuse me, 10 minus 2 is 8. Divided by the 3 seconds gives us about 2.7 meters per second squared. Please remember to box or circle your final answer, and always remember to have units following your answer because units give the number some context. That's important. In number 3, it says, while traveling along a highway, a driver slows from 24 meters per second in 15 seconds to 15 meters per second in 12 seconds. What is the automobile's acceleration? Well, we're going from 24 to 15. 24 to 15. Again, how far we went is not known to us, but we don't care because it didn't ask us. Acceleration is still the unknown we're looking for, and time in this problem is 12 seconds. Well, I'm going to jump right to the acceleration equation that we solved for and derived over here to solve this problem. So final velocity minus initial velocity over time. This time we're going 15 minus 24 over 12. Well, 15 minus 24 gives you negative 9 meters per second over 12 seconds, and that gives you less than a meter per second squared, about negative 0.75. Negative 0.75 meters per second squared. Again, the significance of the negative means that the automobile is moving forward but slowing down as it is doing so. It's called deceleration. All right, in number 4, we have a parachute on a racing dragster opens and changes the speed from 85 meters per second to 45 meters per second in 4.5 seconds. So we are going from 85 to 45 in 4.5 seconds, still looking for acceleration, still don't care about the displacement. Still using the same equation. V equals V naught over T. 45 minus 85 over 12 would be negative 40 meters per second over 12 seconds. Oops, not 12 seconds. My mistake. Sorry, 4.5 seconds. Let me fix that. And negative 40 over 4.5 seconds would be about negative 8.9, or if you wanted to round it up, negative 9 meters per second squared. Again, indicating that the dragster is slowing down, moving forward. In question number 5, it's telling you that the cheetah, which is the fastest land animal, can accelerate from 0 to 70 miles per hour in 3 seconds. What's the acceleration of the cheetah? Well, in this case, we're going from 0 to 70 miles per hour in 3 seconds. What's the acceleration of the cheetah? Again, this is our who cares variable. Well, I'm using the same equation, but this time you're going to notice that the units don't really cancel the way that they once did. 70 miles per hour minus 0 over 3 seconds. And when we divide these three, we get about 23.3 miles per hour per second. Okay, that would be the unit of acceleration when the units don't match up. So we're putting our units in miles per hour per second. Well, in number 6, it's telling us that a Lamborghini Diablo can accelerate from 0 to 99.2 kilometers per hour. So we're going from 0 to 99.2 kilometers per hour in 4 seconds. Again, we want to know the acceleration of the sports car. And let's see. Okay, and now what I'm going to do is I'm going to do a little conversion because I want the units of this to be the same units for the cheetah problem that we just did. So when I convert this, and I can look up in the University of Google to check that out, it turns out that 99.2 kilometers per hour is the same as 61.6 miles per hour. So I'm going to be using that in my calculation instead, 61.6 miles per hour. Okay, I'm using the exact same equation, v final minus v initial over time. V final would be the 61.6 miles per hour minus 0 starting from rest over 4 seconds. And 61.6 divided by 4 is about 15.4 miles per hour per second. Now, if we wanted our answer in kilometers per hour per second, which what the question asks for, I'm just going to do a conversion here. And 15.4 would convert to about 24.8 kilometers per hour per second. So that really is the answer we should have for this question, but I'm getting a little ahead of myself because this answer in particular is going to be what I'm going to use for question 7 to make a comparison. In question 7, which has a greater acceleration, the Cheetah or the Lamborghini Diablo? To figure this out, you must make sure that you're in the same units. Well, the Cheetah has an acceleration of 23.3 miles per hour per second. And that's greater than the car, which has an acceleration of 15.4 miles per hour per second. Okay, so the Cheetah has a greater acceleration in the same time interval. Okay, so now we're going to start solving for other variables. So if we want to find, for instance, the time that it takes or the final speed, then we can use a different equation for it. So v equals v naught plus at if we want to find the final speed. And if we want to solve this for time, I would subtract v naught from both sides like this, and I get v minus v naught equals at. Then by dividing by a, I get an expression for time. Final velocity minus initial velocity over the acceleration. So it's really the same equation we've been using. The difference is acceleration and time have switched places, okay? So keep in mind, we'll go ahead and use both of these equations at various points in time. It's really the same equation, just solved for a different variable. Okay, in number 1, it says a cart rolling down an incline for 5 seconds has an acceleration of 4 meters per second squared. If the cart had beginning speed of 2 meters per second, what's the final speed? So final speed is our unknown. Initial speed was 2 meters per second. 5 seconds this is happening for, and the acceleration was noted as 4 meters per second squared. So v equals v naught plus at, and we plug into it. 2 is the original speed plus 4, and if I show the units here, it's 2 meters per second plus 4 meters per second squared times 5 seconds. And we can see that seconds cancels with one of these, and I'm adding the units of meters per second, right? So we have 20 plus 2. Or 22 meters per second. In question 2, a car accelerates at a rate of 3 meters per second squared. Its original speed is 8 meters per second. How long will it take to reach a final speed of 25? So we're going from 8 to 25, and we want to find out how long that takes. Again, displacement is my who cares variable with an acceleration of 3 meters per second squared. We're going to use the equation we derived above. Final speed, 25, minus the original speed, 8, over 3 meters per second squared, which would be 17 meters per second over 3 seconds. And that gives us about 5.7 seconds. Okay, so if I cancel meters per second squared and meters per second, the only thing left is the unit of seconds. In number 3, it says a car traveling with a speed of 30 meters per second encounters an emergency and comes to a complete stop. Now remember, when something comes to a stop, the final speed is 0. So the original initial speed must have been 30. Okay, I don't know how far we went. It wants to know how much time, that's my main variable, and my deceleration, right, my negative acceleration is -4 meters per second squared. So I'm using the same equation, v minus v naught over a, in which case we're going 0 minus 30 meters per second over -4 meters per second squared. You'll see the negatives cancel, right? Can't have a negative time, right? So if time comes out to be negative, you know you did something wrong. And then dividing those two correctly, we get about 7.5 seconds. And in our last question, it says, if a car can go from 0 to 60 miles per hour in 8 seconds, what would the final speed after 5 seconds if its starting speed were 50 miles per hour? Well, guys, this is a two-part problem. In the first part of this problem, we know everything except the acceleration. Well, we don't know the displacement, but we don't need to know it. We don't know the acceleration. So in step 1, we're going to find the acceleration. This happens in 8 seconds, and we go from 0 to 60 miles per hour in 8 seconds. So acceleration equals change in velocity over time. That would be 60 minus 0 over 8. And 60 divided by 8 is 7.5 miles per hour per second. That's my acceleration, right? Okay, well, why is that necessary? Because it then says, what would the final speed be? Now, that's our main unknown in the problem. Again, we don't know the displacement, but I don't care. After 5 seconds, we have a new time. If its original starting speed were 50 miles per hour. So what's the catch? It's the same acceleration. So what we found here needs to be applied right here, 7.5 miles per hour per second. So using the equation, v equals v naught plus a times t, we plug in values. And we're going 50 miles per hour plus 7.5 miles per hour per second times 5 seconds. You can see the units cancel correctly. And then if we go 7.5 times 5, we get 37.5. Adding that to the 50, we end up with a final speed of 87.5 miles per hour.